Hello. Isn't it crazy how you can hear me right now, even though I'm not right next to you? Well, that's because of sound. During this lesson, we're going to be talking about sound waves. But before we get into what the actual text is, I thought I would do a little bit of show and tell. This is my guitar. You've probably seen me play it. I played it at chapel. It's something that I enjoy playing, and it does a great job of telling us about sound. At the top of this page, I'm on page 233, by the way. At the top of this page, you see the neck of a guitar. I can show you my neck right here, up in the corner. Now, an acoustic guitar, like Mrs. Bulwark's, consists of 6 strings, just like the one in the picture. And what the picture is easy to tell, this webcam image might not, is that the strings have different thickness. And it's because of those thickness, when I pluck it, oh, that was bad. When I hit a string, it makes a different sound or pitch because of the different thickness. I can also put my fingers on different places on the guitar. Oh, my Lanta, that sounded awful. I gotta look at my guitar. I can put, and then strum it together. What I'm doing when I put my hands on the guitar is that I am making the length that the string vibrates shorter and longer. This can change the pitch. Now, one thing that people will sometimes do is hold the guitar like this, and then when I strum it, it makes no noise. Why? When I hold the guitar like this, I am not letting the strings vibrate, and it is the vibration that helps create the sound. So, sound, according to your textbook on page 233, is a wave of vibrations that spreads from its source. A vibration is back and forth motion of an object. You can really see it on a guitar. You can see that string moving back and forth. As sound waves travel, the molecules in the material will vibrate in a regular pattern. Right now, as I am talking to you, I have waves coming out from my mouth that are bouncing off of the particles in the air, vibrating through them in order to create sound. Sound waves are what we would call mechanical waves, in the fact that they need something to travel through. If nothing is there, they cannot travel through it. When we are singing, our vocal cords vibrate, same as when we talk. Vocal cords make the particles in the air around them vibrate. We have them in our throat right here, and they vibrate. That causes us to speak when those vibrations travel out through the air. Sound waves can travel in all directions. You have this girl, and it says even someone behind the girl can hear her singing. All right. How are vocal cords and strings on a guitar alike and different? Both of them involve vibration. So both of them use vibration. My vocal cords are vibrating. Strings on a guitar will also vibrate. However, I pluck a guitar, right? I'm not plucking my throat or my vocal cords, right? I don't pluck my vocal cords. But I do pluck a guitar. So that's one of the ways that they are different. So, second question. Infer. The girl is playing a guitar. Well, doesn't look like she's playing one in the picture, but she's holding a guitar. How could she stop the sound after she plucks the string? So, How do you stop the sound after you pluck the string? Do you remember what Mrs. Bulwark did? If you press the string and stop it vibrating, the sound will also stop. So if I press the string and stop it from vibrating, the sound will also stop. Because sound waves require vibration. So stop the vibration, you don't have any sound. Let's turn the page. Like I said about sound, sound needs to travel through something. It can travel through solids, liquids, and gases. If there is no solid, liquid, or a gas, sound can't travel. They give you the example of a vacuum. Do you know examples of a vacuum? And I'm not talking about the thing you use to clean up, but something with no gas, no liquid, no solid. Outer space. Outer space is a vacuum. When we talked about outer space, we talked about how these satellites, these probes that we send out, have inertia and don't need to use fuel, that they'll just keep on going because there's nothing to slow them down. There is no air in outer space. Because of that, there is no sound in outer space. It cannot travel through. When a sound wave reaches a border between different materials, it might bounce back. When we have a sound wave that bounces back at us, we call that an echo. Sometimes sound waves are absorbed or passed into the second material. This is how soundproofing works. Sound waves are able to be trapped in certain materials. We see that with YouTubers and recording studios for musicians. In order to stop the echo, they put things on their wall that will trap sound. Sound waves also travel through different materials at different speeds. In ocean water, sound travels 1,500 meters per second. In air, at 0 degrees Celsius, that's freezing, sound travels at 330 meters per second. You hear sounds when waves of vibration reach your ear as well, and we can see what the waves look like for sound. We have compressions, which is where they're close together, and the opposite of compressions are called rarefactions. And this is all what we are going into to hear our ear. Sorry, that didn't make any sense. This is all the sound waves vibrating into our ear. Now it shows us that wavelength is the period of one wave to another, and compression we have here, waves are close together. We call those compressions. The number of compressions that pass by a point each section is called the wave's frequency. Frequency is a measure of how other particles are vibrating, slow or fast. The greater the frequency, the higher the pitch. So when I talk like this, my frequency is a lot faster, you know? Because my pitch is a lot higher. And when I talk like this, my frequency is lower. Smaller animals and objects make sounds with higher pitches than large animals and objects. In fact, some animals can make pitches so high that we cannot detect them with our ears. Do you know an example of one? That's right, bats. Bats. Echolocation. That's what they use. Now, when it comes to volume, we know that's how loud or how soft something is. The sound waves of a louder sound have more energy when they get to your ear. This is because we are close to the source of the sound. It could also be because it's vibrating more. More vibrations, louder sound. When the higher energy gets to our eardrum is also going to vibrate more than if the sound were softer. I want you to experiment today with high pitch and low pitch and volume, not by driving people in your house crazy, but if you look at the beginning of this section, I didn't make this required because I don't know if we have all the supplies at your house. If you do have rubber bands You can put them over an empty Kleenex box. You can put them over a plastic tub, and then try plucking them to see if, and then you can mix a ruler in as well. Pluck them and look at the vibrations. That's visible vibrations of sound waves that we can see. And so if you have time at home, go ahead and try this. It's really cool. Tomorrow we are going to finish this section and we are going to fill in some of these blanks. Remember, sound needs to travel through something like air or gas, liquids, and solids. Sound cannot travel in outer space, which is a vacuum. Sound waves travel through vibration of particles. Pitch, the higher the pitch, the greater the frequency. Frequency is how fast waves are moving. If they're vibrating more or vibrating less, that will impact the volume of the sound. Sound can also travel through different things at different speeds. If you want to, you can put your ear down to the table and tap, tap, tap and say what you hear, because you're hearing sound travel through that table. All right, I will talk to you more later. Hopefully the sound on this recording went okay. Bye.